Hi everyone. Let's talk about inscribed angles in circles. Last week we talked about central angles. A central angle is an angle whose vertex is at the center of a circle. And as we discussed, the measure of an arc is equal to the measure of the central angle that intercepts that arc. Last week we looked at a diagram like this, where we had this diameter, xb, and we looked at this angle right here, AXB. And it turned out that this kind of had a nice relationship in that this angle was half the measure of the central angle. And so this angle had measure half the measure of the intercepted arc. Now, there's a neat reason why this is true in this particular diagram. You have this diameter here. You can draw these radii. This is an isosceles triangle. So this angle right here is congruent to this angle. And this angle is exterior to this triangle. So it's equal to the sum of the two remote interior angles, which are congruent. So each is half of this. So in this particular situation, this angle right here is half of this angle. This is called an inscribed angle. An inscribed angle is an angle whose vertex lies on the circle. So contrast that with a central angle. Central angle, vertex at the center, inscribed angle, vertex on the circle itself. And as it turns out, there's a really beautiful relationship between the measure of an inscribed angle and the measure of the arc that it intercepts. So here we have a more general inscribed angle, one that's not part of a diameter. And let's just turn on the angle measures here, and we'll bring this angle back. And if you take a look, this angle right here, this inscribed angle, has a measure that is half of this central angle, and therefore this inscribed angle's measure is half the measure of its arc that it intercepts. And we can change the arc a little bit. Let's try to make it 60 or so, pretty close. And you can see that this is right around 30. And what's interesting is, no matter where we move this point, the vertex of our inscribed angle, that angle is still equal in measure to half of this arc, which has measure 60.3. So this is called the inscribed angle theorem, and this is one of the most powerful angle theorems in circles. The measure of an inscribed angle is equal to half the measure of the intercepted arc. So that's the inscribed angle theorem. And this theorem has a lot of immediate consequences. For example, if we take another inscribed angle that intercepts the same arc, then these angles must be congruent because each of their measures is equal to half the measure of this arc. Therefore, they're the same angle. Another consequence is that if you have two inscribed angles that intercept congruent arcs in a circle, then those two angles are congruent because they intercept congruent arcs. Those inscribed angles have the same measure, and therefore they're congruent. So the inscribed angle theorem says the measure of an inscribed angle is half the measure of the intercepted arc. Here we see that that's true because of this isosceles triangle in the exterior angle theorem. We were able to do this because this is a diameter. We don't have a diameter here, but the key to proving the inscribed angle theorem is to get a diameter, and we'll do that just by drawing one in. Now, the way we're going to prove the inscribed angle theorem, namely that this is equal to half the measure of this, is to use the argument we just used here twice. Here, on this side, this angle is half of this, because this is an isosceles triangle. These angles are congruent. They add up to this. And this is the central angle for that arc. So this is half of this, and this is half of this. So when you add them together, that will be half of that. And so in this situation, you can draw the diameter in and apply that theorem that we just used here twice to prove the inscribed angle theorem. Now, if let's say we had the vertex of the angle over here, we could apply the same idea by drawing the diameter in. Now we can find the measure of this angle using that same principle. That's going to be half of this arc. And then we can just subtract the measure of this angle, which is half of this arc, to get the fact that this is half of that. So this is how we would prove the inscribed angle theorem. One of the neatest consequences of the inscribed angle theorem is this situation right here. So notice AB is a diameter of the circle. X is an inscribed angle whose endpoints, or whose arc, is this semicircle right here, which is cut off by this diameter. Therefore, the measure of X has to be half the measure of this arc, but a semicircle has measure 180 degrees, which makes this a right angle. So another consequence of the inscribed angle theorem is that an inscribed angle that intercepts a semicircle must be a right angle. So all of these angles are right angles. And if you remember, we've talked about this situation before a little bit. If I reflect this point through the center, I now have another inscribed angle intercepting a semicircle. This is a right angle, and of course this figure right here is a rectangle.